Hi, I'm Dr. Incognito. In this video, we're going to examine limits at infinity. Limits at infinity means we're going to be looking at the limit as x goes to infinity of f of x, or the limit as x goes to minus infinity of f of x. And probably the single most important example of such a limit is this one, the limit as x goes to infinity of 1 over x. The limit as x goes to infinity of 1 over x. And this limit is 0, so let's talk about that. What this is saying is as x grows without bound, then its reciprocal will shrink to 0. If we look at some values of x and 1 over x, that will probably be clear. If x is 10, which isn't really very big here, then 1 over x is 1/10, which is 0.1. If x is 100, then 1 over x is 0.01. We can see it shrinking, getting closer to 0. If x is 1,000, then here we have 0.001. And now if we make x something like 1,000,000, then we have 1 over x is 0.000001, which is a teeny tiny little positive number. So as the x grows, 1 over x, its reciprocal, will shrink. And so as x grows without bound, the reciprocal is approaching 0. And this information has graphical implications. This limit at infinity being 0 tells us that the line y equals 0 is a horizontal asymptote for the graph of y equals 1 over x. So y equals 0 is the x-axis. And the x-axis in this case is a horizontal asymptote for the graph of y equals 1 over x. So as x goes to infinity, 1 over x will shrink to 0. That will give us a horizontal asymptote in the graph. Let's look at some other examples. How about the limit as x goes to infinity of x squared? As x goes to infinity, so x is growing without bound, x squared will be even bigger. If x is 100, then x squared will be 10,000. So as x grows, x squared is going to be even bigger. It's going to grow. And so as x goes to infinity, x squared will go to infinity. And that's also indicated in the graph. As x goes to infinity, the y-coordinate is also going up and up and up to infinity. How about the limit as x goes to minus infinity of x cubed? As x goes to minus infinity, so x is a large negative number. If x is negative 100, then y would be x cubed. When you cube a negative, you get a negative, so it would be negative 100 cubed, and that would end up being negative 1,000,000. So when x is negative, x cubed will be negative, and as the x grows, the x cubed will grow. So as x goes to minus infinity, x cubed will also go to minus infinity. The graph of x cubed bears that out. The graph of x cubed looks something like this. So as the x goes to the left, the y-coordinates go down. As the x goes to the left, the y-coordinates go down. X goes to minus infinity, x cubed goes to minus infinity. So in those last two examples, we didn't have a horizontal asymptote. because the limits were not numbers. For x squared, the limit was infinity. There's no horizontal asymptote there. And x cubed, as x went to minus infinity, the limit was minus infinity, so no horizontal asymptote there. In order to get a horizontal asymptote, the limit had to be a number. This horizontal asymptote, the limit was 0. The limit as x went to infinity of 1 over x was 0. How about the limit as x goes to infinity of e to the negative x? E to the negative x. So e here is a number between 2 and 3. We'll think of it as being about 2.7. And so what does it mean to say something like e to the negative 10? E to the negative 10, because we have a negative exponent, that means 1 over e to the 10. And e to the 10 is several thousand. So 1 over a number that's several thousand here is a small number. And if we do e to the power minus 100, that would be 1 over e to the power 100. E to the 10 was several thousand. E to the 100 is an astronomically large number. So this is, the reciprocal then is a tiny number. It's much smaller than 1 over e to the 10. And so maybe you can guess then that as x gets bigger, as the x gets bigger, e to the x will get bigger, and so its reciprocal will get smaller. So this limit will be 0. In the same vein that this one was 0, because when we're looking at the limit as x goes to infinity of e to the negative x, we could write it in a similar form here. We could say it's the limit as x goes to infinity of 1 over e to the x. And as x grows, e to the x grows very quickly, and so the reciprocal will shrink very rapidly. In the same way that 1 over x shrank to 0, 1 over e to the x will also shrink to 0. And so again, y equals 0 will be a horizontal asymptote for, in this case, the curve is y equals e to the negative x. But the graph is different. Let me draw the graph of y equals e to the negative x. It's actually very similar, but it didn't have a vertical asymptote there. The graph of y equals e to the negative x looks something like that. The line y equals 0 is a horizontal asymptote on the right end. As x goes to infinity, e to the negative x goes to 0. Another example, let's take a look at the logarithm. Y equals the natural log of x. The graph has a vertical asymptote on the y-axis. What is the limit as x goes to infinity of the natural log of x? So the natural log of x curve kind of tails off. It looks like it might have a horizontal asymptote, but actually it does not. As x goes to infinity, the y-coordinates will keep growing. This answer will be infinity. For example, if you want this curve to have a height of 10, then the input you need to put in is e to the 10. The natural log of e to the 10 is 10. If you want this curve to have a height of 100, then the input you need to put in is e to the 100. The natural log of e to the 100 is 100. So you can make this curve as tall as you like. You can make it 1,000,000 or 1,000,000,000 by putting e to that number, e to the million or e to the billion in. Then the log will give you the million or billion back out. Interestingly, this number, the scale is a little off here. E to the 10 would be in the thousands. This is 1, although 1 is 0. E to the 1,000,000, if that is our spacing for 1 unit, they're about 2 inches, then e to the 1,000,000 would take you to the outer edges of the known universe. So you have to be pretty far to the right there in order to get the curve up to a height of 100. But mathematically speaking, nonetheless, the curve does reach the height 100, and there is no horizontal asymptote. The limit of the log as x goes to infinity is infinity. And let's look at one more familiar function. Let's look at the sine function. What is the limit as x approaches infinity of sine x? The sine function has this this repetitive oscillatory behavior. It oscillates between the heights -1 and 1 every 2 pi units. So as x goes to infinity, the sine of x, it's not going to infinity, it's not going to minus infinity, it's not heading to 0 either, it's just wobbling back and forth between -1 and 1. So it's not approaching any fixed number. We say that this limit does not exist, and the reason is due to oscillation. One last interesting function, somewhat familiar function. Let's look at the inverse tangent. The limit as x goes to infinity of the inverse tangent of x. This one requires a familiarity with the tangent function. If you draw y equals the tangent of x, then here's negative pi over 2, pi over 2. It has vertical asymptotes, and the curve, you can see that there's a vertical asymptote at pi over 2 and a vertical asymptote at minus pi over 2. And because of those, the inverse tangent has, when x goes to infinity, the inverse tangent goes to pi over 2, corresponding to this vertical asymptote. And on the other end, the limit as x goes to negative infinity of the inverse tangent of x is negative pi over 2. The graph of the function y equals inverse tangent of x can be taken from this graph by reflecting about the line y equals x. When you're making graphing an inverse, you draw the line y equals x, and then you reflect the tangent curve in that line, and you get the inverse tangent curve. So the reflection of a vertical line in the line y equals x will end up being a horizontal line. This will be the line y equals pi over 2, and the other vertical asymptote will be the line y equals negative pi over 2. And the curve, the inverse tangent, will look like this. So we see there are two different horizontal asymptotes. On the right end, the line y equals pi over 2 is a horizontal asymptote. That's on this end. And on the left end, as x goes to minus infinity, the line y equals minus pi over 2 is a horizontal asymptote. So there are two different horizontal asymptotes. So that's an interesting example of limits at infinity. Okay, thank you for watching.